So corroded bars will, the powder, I don't know if you have played with the powder of corroded products, corrosion product, it's like powder. It's like a lubricant. You can just pull it, it comes apart. Okay, very easy. So the pull-out strength is completely lost for this kind of reinforcing bars, and that's the problem for steel reinforced bars. Therefore, our FRP can replace this kind of reinforcing bars. But FRP, I mentioned this once, but FRP is very, very weak. FRP bars, very weak in compression. So our ACI guidelines tell us not to use compressive strength of FRP bars in your design. So in our design, any member design, we will never ever use FRP compressive strength in the calculation of strength, member strength. Not going to happen. So in columns like this, you still need some reinforcing bars. Maybe you can provide, FRP bars with steel reinforcement, but steel is the material that must be used in columns like this. So spalling is a problem, right? For corrosion, these are hoops. The hoops will snap, and this. Sorry, I don't want to treat you like my undergraduate students, but when your hoops corrode, there are two problems. One problem is the cover concrete spalls off, therefore the area becomes smaller, right? So you lose some strength from just compressive strength related to the spalled concrete. You lose some strength. You'll also lose some other strength. Can you tell me what is the lost strength? If the hoops are corroded, they are not effective anymore, what happens? Confinement effect is gone. So what's the effect on design? That's correct. What you say is right. Toughness is not what, okay, we are talking about strength, axial load strength. Buckling is a problem, but there is another problem. When you are designing your columns, you classify them as tied columns and confined columns, right? So there are different strengths. So if your hoops are lost, then you have to design it as a tied column. So the strength of a tied column is about 80% of confined column. Are you with me? So you will be using, you have to use a smaller strength when the hoops are gone. That's the real difference, actually. So anyway, coming back to our corrosion problems, this is a real bridge which is in operation, actually. There's traffic here, everything. It's very close to that Pittsburgh temple in Monroeville, near Pittsburgh. Okay, so it's really in bad shape. I know some of us, while talking, we say, oh, we have a lot of coastal structures. They're all corroding and they're in very bad shape. I want to show you these pictures because even in US, there are lots and lots of this kind of bridges. Okay, they are functional. People are using it. See this. This is the real bridge. Okay. So all these strands, those of you who are familiar with pre-stressing strands, they are all snapped. And the shear reinforcement is gone. Okay. All right. And this corner here, this concrete, chunk of concrete can fall anytime. It's totally detached. So there is a story to this. I took pictures, these pictures, same pictures, and I posted. Those days it was Flickr. So I posted it on Flickr and said, what a disgrace. That was my caption. I said, what a disgrace. And I put all these pictures. Somebody noticed it. And after 6 months, they started working on it. I don't know if it is my effort, but I'll take the credit anyway. So they fixed it. Now they fixed it completely. So this is how it looks, the column completely losing its cross-sectional area and everything. So these are some of the shear reinforcing bars. I mean, that's the U bars. That's not closed loops, U bars. Place it from the bottom, place it from the top. That's what it looks like. These are older bridges. That's the detail they used to use previously. And these surface, you can see these shear reinforcement is completely gone. And that's not a good thing. Anyway, they fixed it. So why do we need to use composites in structures? That's our next question. So I presented a lot of advantages. Any questions so far? Yes. Can you speak up? Absolutely. Yes. We'll talk about it. Excellent. We'll talk about it because that's a big limitation. So the question was, FRP bars, you cannot just bend them like you do in steel bars. So, yes, it is. I agree. I will talk about it in a minute. So, in steel bars, in steel reinforcement, shear reinforcement particularly, what they do is they use 12 millimeter, maximum 16 millimeter bars. You can use for shear reinforcement. At least the practice, American practice is not to use larger diameter bars for shear reinforcement. The reason for that is you can easily bend edge side, not easily, but with some effort you can bend it at side if it is 16 millimeter or smaller. If it is larger than 16 millimeter, you just can't, no matter what tools you have, you cannot bend it at side. So that's the reason normally they use about 16, 12 millimeter bars. Okay, so that flexibility you have for steel stirrups. Whereas for FRP, we'll talk about it, that flexibility is not available. We'll talk about it. I'm glad you brought it up. I'll definitely talk about it. It's a big deal. Okay, so any other question? Okay, so most important factor in steel corrodes, so durability is an issue, therefore FRP is a better solution. Lightweight for sure. Actually, those of you who are more concerned about environment, you can always say lighter the material, smaller the carbon footprint. There are a lot of ways to prove that it is environmentally better, but it's very expensive. So environmental benefit by itself cannot sell FRP bars. And the advantages are high specific strength and modulus. Maybe not modulus as much. We'll talk about that. Durability, corrosion resistance, and so on and so forth. Okay. So, in some places, some applications, it is really, really advantageous to use FRP bars. Like in hospitals, these days, you will always have an MRI room where they do all your scans and stuff like that. Okay, they are very, very sensitive to electrical disturbance. Put it that way, simply. Any magnetic interference will make a big difference to the results they get. So they don't want anything steel in MRI rooms. That's where, no matter how expensive it is, you can still use it. In America, they use almost all MRI buildings. They use these days. They are using non-magnetic materials, and FRP is one of those. Okay, so if you are thinking of any application, and there are lots of hospitals coming up in India. Every corner you have huge hospital, right? So you'll probably be working on some of those designs yourself. You can always consider FRP as an alternative. Does it make sense? So that's your MRI rooms. That's a very big application. Cables for suspension bridges, they're slightly different types. Don't worry about that. Internal reinforcement. I will show you, what time is it now? 12:10.